I think it's a good time to start now. It is an absolute pleasure and honor for me to introduce our third qmeets speakers, Martin Plenio and Dayou Yang. Let me say a few words about the two, and then, of course, we are eager to listen to their talks. So, I found it actually quite hard to write a concise summary about Martin Plenio's research activities. So therefore, I thought I'd just pick a few things that I personally find extremely interesting. So for those of you who don't know him, he's the director of the Institute of Theoretical Physics in Ulm and founded also the Center of Quantum Bioscience. As one of, unfortunately, not many physicists, he also co-founded two companies, QC Design and Envision, from academic findings. And his research interests sorry, are extremely broad, actually. So one big part is concerned with a resource theoretic or operational approach to quantum phenomena. In early days, more focused on entanglement measures, but also on coherence. And it's also related to quantifying open quantum systems and their dynamics, especially beyond Markovianity. During quite some time, he also worked on entanglement in many body systems, a topic that I personally like a lot. Area laws is a key word here, but he's also very interested in quantum biology, so understanding how quantum effects play a role in, for instance, photosynthesis or chiral-induced spin selectivity. There is ongoing stuff in quantum computing, in particular in a platform called Nitrogen Vacancy Centers in Diamond, also linked to other people in Ulm. And more recently, if this list is not long enough yet, the question, can we say something about whether gravity is quantum or not? Were remarkable contributions deciding when the gravitational interaction can be described by an LOCC and when not. On the other side, we have Dayou. He did his PhD in the group of Peter Soller and then went to Ulm 2019. And just, I think, 2 weeks, 3 weeks ago, something like this, he went to Shanghai, to the University of Science and Technology of China, to start his new position there. And Martin and Dayou, over the last couple of years, focused a lot on the topics quantum metrology and sensing, and in particular on quantum sensors considered as driven and open quantum systems. They made very nice and remarkable contributions to the case where these sensors are continuously measured. So for instance, when you continuously count photons or something like this, and found theoretically very nice results on when the measurement limits, so how precise you can measure something, become tight and how to make them as tight as possible. And with this, I thank the two of you for agreeing to give talks today, and the stage is yours.
Okay, thank you very much. Thanks for inviting us and to this qmeets seminar. I like the concept, so I was very happy to contribute to it. And indeed, so I will give the introductory presentation to give you some perspectives of quantum sensing and metrology, and really basically give you a bit of where the research project that we then were pursuing with Dayou came from, in a way. You know, what's the motivation for it? And so this is work that so Dayou and I, of course, did, but also I should mention Susanna Welga, also professor at the Institute, who was heavily involved in all of these works in this project and metrology in particular. Okay, so here, by the way, you see on the front side, on the front page, you see the Center for Quantum Biosciences. where we bring together researchers from experimental physics, theoretical physics, organic chemistry, and virology, um, to try and bring quantum technology to the life sciences, basically. And right, so let's get started. And that's actually already, in a way, start of the motivation. So, I mean, many of you know, and if you read the newspapers, you will all the time read about people building quantum computers or wanting to build quantum computers. And we all know that this is a fantastic challenge, a fantastic endeavor, but it's also fantastically difficult because you will need to control millions, if not billions, of physical qubits. And that's a really big control challenge. But for metrology and sensing, on the other hand, we know that with a small number of qubits, we can already make a difference. Yeah, maybe a handful, maybe even one, but maybe a handful of qubits. And that can really make a difference, not because it gives you an exponential advantage over classical physics, but maybe only a factor of 10. But a factor of 10 allows you to see things that you could not see before. And this may enable to you to see novel structures in the life sciences. Okay, and so that's the starting motivation for looking into quantum systems, a handful of quantum systems as sensors to learn new things about the life sciences. And where does this come from, actually? And really, this sounds like a brand new story, but this is not really so new. And if you go back and if you go back a few hundred years, um, there's Galileo Galilei, and he learned about this new instrument, the telescope. And there, what happened was that scientists started to control light using lenses. Yeah? And so they started to understand how diffraction worked and how refraction, all these things worked. And they turned this knowledge, this understanding, into a technical device. And that is a telescope. And so that's what Galileo used. He looked at the moon. This is how the moon looks for us. So we see that there's some structure for it, but it looks pretty round, actually. So what he, with the telescope, managed was to go closer, so to speak. And he actually saw that the moon is not round. Actually, it has mountains. He realized this by the shadow that they were throwing on the moon. And he could even estimate their size. So this is what Galileo was able to do with this new technology that natural scientists at the time, they were not called physicists yet, developed. But then something remarkable happened, because here you can say, well, we see the moon anyway. We know that it's there. It's not really new. We learned a little bit more detail maybe. But then actually a Dutch scientist, van Leeuwenhoek, he thought, okay, if I can magnify the moon, that's interesting, but let's try to magnify small things. Just let's build a microscope instead of a telescope and magnify small things. And so he was the best microscope maker in the world at that time. So his ways of building microscopes took 50 years to find out all the secrets that he had found, because he never published them properly. So he controlled light also by lenses, and he looked at little puddles of water, and he discovered something that nobody even knew that it was there, and this was bacteria. So he was the first person to see bacteria thanks to a physics technology. Okay, so that's very nice, and people were of course amazed at that time. So this was a sensation, absolute sensation. So Robert Hooke, from Hooke's law, he was an extremely eminent physicist at the time, president of the Royal Society and so on. And he thought, okay, by the help of microscopes, there's nothing so small as to escape our inquiry. They just thought, okay, we improve microscopes more and more, and we will see smaller and smaller things. But of course, we know it's not quite so easy. Yeah, but in the end, of course, in a way, over the next centuries, such a development took place. Because what happened was, okay, we start with microscopes, but then people, for example, learned to control electrons. So they discovered electrons. They learned how to control them with microwave, with magnetic fields and electric fields and so on. And they built the electron microscope. And in between, before that, there was also Konrad Röntgen, who discovered the X-rays, and he could look into the body. And again, so physics technology, new laws of physics were discovered. We learned to control them, and we turned them into a technological device that allowed us to look into biology. The next thing was, okay, that was X-rays, but not for looking into the body, but for making X-ray crystallography. So people had to understand diffraction very well and also actually use quite a bit of computational techniques. But that was actually used to determine DNA structure. Our understanding that DNA is a double helix comes from X-ray diffraction. And another thing that people discovered was nuclear spin. And then the fact that using magnetic fields and radio frequency fields, you can manipulate nuclear spins and you can do nuclear magnetic resonance. And so again, you can learn something in this case about protein structure. Lots of protein structures that we know now are from NMR. So every time over the last few centuries, physicists understood natural laws. This was often an abstract endeavor supported by experiments. Then they took this knowledge to learn to control the natural phenomena, and they turned them into observational devices to do sensing and metrology. And now, of course, the question is, where do we go next? What would be wonderful goals that we could pursue, and what technology could we use to do so? And here are two examples that I find quite exciting and that we are also pursuing together with experimentalists. So on the one hand, we would like to actually push nuclear magnetic resonance from the typical volumes of, let's say, cubic centimeters or so, to be able to actually do nuclear magnetic resonance on a single cell. And for that, we need better magnetic field sensors. So we need to improve our quantum sensors by several orders of magnitude to have enough sensitivity to see the signal from a single cell. And on the other hand, what would also be really exciting would be if we could have magnetic field sensors that are super sensitive so that they can actually look and measure look at our brain and measure the magnetic field emanating from the brain. So doing magnetoencephalography, but using this by using quantum detected quantum sensors to achieve this. And again, for this, we have to really push the boundaries and make better sensors to get access to these very, very weak signals. But if we can do this, and if we can make this very small, I mean, very compact in terms of devices, then maybe eventually we will be able to build human-machine interfaces where we put on a helmet or maybe a very thin helmet, and then this helmet is full of these detectors. It measures the magnetic field. And then maybe with AI, we learn how to interpret this, and we can control maybe devices just by our thoughts. And so this is not completely crazy. So people already starting to build this, but to really turn this into an everyday device, we still need to improve these sensors. Okay. So this is, for me, these are sort of holy grails that we would love to achieve, maybe 10 years down the line or so. But for that, we now need to think about better sensors. And now you can wonder, well, okay, why do we think that sensors will actually get better and better? And for that, I would like to take another look at, at history. And I think all of you know, and all of you have heard about Moore's law. Moore's law says that the computational power that you can buy for $1,000 actually increases exponentially in time. So every 18 months or so, the computational power doubles, roughly. And it's interesting that Moore actually proposed this in the 1970s. But actually, you can go back historically even further until the early end of the beginning of the 20th century. And you can really make a chart of our ability to process information with mechanical devices first, then with solid state relays, then with vacuum tubes and transistors and then integrated circuit. And actually, since 1900, our computational power is growing exponentially already in time. Well, this is actually quite amazing. And now you could say, well, okay, this is true for microprocessors. Is it also true for our ability to sense and measure things? And actually, you can make similar charts. They're much less famous. They don't have a name to them. But you can look, for example, at our ability to measure time. And then first we had mechanical clocks. And there, it took us about 400 years or so to improve their precision by a factor of 10 or something like that. Then eventually, there were pendulum clocks. So they used already a periodic process to measure time. And what you see here is now that the rate of improvement is actually accelerating. So now actually to gain another factor of 10 took us only about a century or something like that, or much faster already. Today, we are using atomic clocks where we use individual atoms. And the rate of improvement is even faster. And in the rate of improvement, so it's again an exponential law. So again, also our ability to measure time grows exponentially with, chronological time. So that's actually quite impressive. And what we should realize here is also that this improvement in our ability to measure time grows exponentially and seems to be really going on and on and on. But the underlying technology is changing every time. So to keep this going, we need to change the underlying technology. First, mechanical clocks, then, pendulum clocks, then atomic clocks, and so on. And so, of course, we want to take the next step. We may have to introduce a new technology. And so that drives me back to the magnetic fields. For that, I couldn't even find a plot in the internet, so I had to do one myself. So I sat down a few days ago and collected numbers. And it's the same thing. First, we measured magnetic field by a compass needle. That was really very imprecise. But then there was a galvanometer. It was introduced by Gauss, actually. And again, there was an exponential improvement. And then, okay, I left out some things, but then in the 50s or so, optically pumped magnetometers were introduced. And the rate of improvement and sensitivity, well, is accelerated. Then squids came along and things accelerated even further. And so this is what we want to continue now. We want to really go and develop the next technology that not only will be better than squids, but actually will also improve the rate of acceleration of our ability to sense magnetic fields. And for that, of course, we use quantum sensors, and initially we would use individual atoms, perhaps, and that has the advantage that they have a very high frequency of oscillation, so to speak, that makes them very sensitive to magnetic fields, but they're also very small, so we get spatial resolution. But that has its limits. So what we really want to push is that we want to go from individual quantum systems to a large number of quantum systems. So, and this can be done in two ways. Either we just pack a lot of atoms together and use them individually to measure magnetic fields and then do statistical averaging and increase our sensitivity. If we do that, then the sensitivity improves like 1/square root of the number of quantum systems that we are using. This is already good, and this is what these optically pumped magnetometers are actually using, but this is not good enough. What we want to use is we want to also use quantum correlations to actually then improve this scaling from 1/square root of n to 1/n. So that's what we can achieve by using really entangled multi-particle systems. And so that, of course, can make a huge difference. If you imagine I have 10 to the 8 particles, and I have a 1/square root of n scaling or a 1/n scaling, I gain a factor of 10,000. So there's really a lot to be gained by starting to learn how to control the quantum correlations of particles to make really even more precise sensing devices. Okay, and so the dream for me would be to build such devices to then solve these challenges that I had put on the whatever the second or third slide, namely single cell NMR or building this human machine interface. And maybe, and what is quite likely, we will, once we have these devices, we will actually find other things that we want to measure that are even more exciting, that we cannot even think of now at the moment, but that will become available by having these new sensing devices. And so that's the motivation. And that's what basically set us going when Dayou arrived in Ulm, that we wanted to see and we wanted to find out how we can really make these super advanced quantum sensors building on quantum correlations. So that's my part of the story. And now I would say, Dayou, unless there are urgent questions immediately, Dayou would tell you how this can be done and what we have found in those years.
Good, good. Thanks, qmeets, for inviting us. Thanks, Martin, for the very nice introduction. Now let's proceed to the second part of the seminar, where I will introduce you a few examples selected from our recent research that gives you an impression of how fundamental quantum phenomena, for example, quantum noise and many-body correlation, fundamentally determine the performance limit of quantum sensors. The title of the second part is Quantum Noise Reduction Techniques, because as you will see, the performance improvement of quantum sensors fundamentally rely on the suppression of its quantum noise. So here is a schematic of an optical interferometer that is very similar to a gravitational wave detector. The tiny movement of the end mirrors of the interferometer imprint a phase shift to the outgoing light that can be measured by phase-sensitive detection. If we look at the detected data, we see a position-dependent phase, that is our signal, and on top of it, there are abundant noise. They have different origin. Some are thermal noise due to the thermal fluctuation of our experimental device, as well as the electronics. And some are technical noise due to the vibration of the surroundings, for example, or even due to the movement of the Earth. And finally, there is a little bit contribution that is due to the intrinsic quantum fluctuation of the sensor device. For example, for this interferometer, it is the quantum fluctuation of the laser, which we know is described by quantum mechanically as a coherent state. Scientists have been working very hard for decades in order to improve the precision of sensors by removing the excess noise as much as possible. And only until recent decades, they managed to remove most of the thermal and technical noise. As a result, the remaining dominant noise now is the quantum noise. Such quantum noise limited precision is the defining feature of quantum sensors. There are not so many sensors that enter this regime yet. Another important example is the atomic clock, which provides us the most precise estimation of the internal transition frequency of atoms. In that scenario, the dominant quantum noise is the spin projection noise. So what is the precision limit of quantum sensors? Martin just introduced us. Many of quantum sensors are limited by the so-called standard quantum limit. Taking again the example of optical interferometer, as I mentioned, the state of the laser is a coherent state, which is plotted in this figure in the phase space as a distribution. The distribution is displaced from the origin by the square root of the mean photon flux of the laser, and the width of the distribution represents the quantum fluctuation of the laser, which is of order 1. As such, the uncertainty of phase estimation is inversely proportional to the mean photon flux of the laser. And similarly, for atomic clocks, the uncertainty is inversely proportional to the number of atoms in the clock. Such a scaling, inversely proportional to the number of particles of the sensor, is what Martin just mentioned, the standard quantum limit. I want to emphasize that the achievement of the standard quantum limit is already very challenging experimentally, and there are not so many platforms that have demonstrated such a precision scaling. It requires the suppression of all the technical noise such that the quantum noise dominates. However, we physicists are never satisfied with what we have achieved. With quantum noise limited sensor at hand, we are about to ask the question, how can we further improve the precision of sensors by reducing the residual noise? Now it is the quantum noise. So how can we reduce the quantum noise? One way that people are aware of is the use of highly entangled many particle states. In principle, if we are able to generate squeezed state with squeezing strength increasing with the number of particles, or if we are able to generate GHZ-type entangled state for sufficiently large particle number, then we can achieve a precision scaling that is inversely proportional to the number of particles. It has a factor of square root of n enhancement, as Martin mentioned, compared to the standard quantum limit. And this is called the Heisenberg limit, which is the ultimate precision scaling allowed by quantum mechanics. However, the experimental generation of this highly entangled state for large particle number is very challenging. Moreover, this highly entangled state becomes increasingly fragile to environmental decoherence with increasing particle number. So a central challenge to quantum metrology theorists like me is to come up with novel methods to reduce the quantum noise. And this method should be technically not that demanding and should be robust against environmental decoherence. In the following, I will introduce you a few examples selected from our recent theoretical work to give you a taste of what these alternative new approaches are. So some quantum noise can be cancelled via destructive quantum interference. And this is spiritually similar to the classical scenario where we wear a noise-canceling headphone to cancel the environmental noise. For this purpose, the headphone detects the noise from our surrounding environment and generates accordingly some additional noise that exactly cancels the original one. We can extend this principle to the quantum regime to cancel a kind of noise that is dynamically generated during the continuous measurement process. The scenario is like this. We have a quantum sensor that is evolving under its Hamiltonian Hs, and it is interfaced with quantum light via its jump operator, Js. This sensor is coupled with some unknown parameter phi. Here, phi is not necessarily be a phase, and it can be a general parameter that we wish to estimate. We estimate phi by the detection of the output light of the sensor. This scenario captures the operation principle of a broad class of important sensor technology. For example, the gravitational wave detector, which consists of moving mirrors interfaced with laser light, and also atomic gas magnetometer that is made of atomic cloud driven by the laser, as well as driven dissipative Rydberg sensor. Moreover, in nanoscale NMR, we use an MV center to perform sequential weak measurement of surrounding nuclear spins, which also mimics continuous measurement. For continuously monitored quantum sensors, it is generally very challenging to unlock their optimal performance. This is because there are extra quantum noise in the output field of the sensor device. The input field is our laser, and it has very simple quantum noise property. It's basically the quantum fluctuation of the coherent field. But after light scattering with the sensor device, the output light contains complex colored quantum noise. Such noise can be reviewed by the temporal correlation function of the output light, as written here. Via the quantum optical input-output relation, such correlation can be traced back to the autocorrelator of the sensor itself, which can be rather complex. By measuring the output photons, either we do photon counting to register the arrival time of each photon at our photon detector, or we perform homodyne measurement to register the instantaneous phase of the output light. Such extra quantum noise then enters our measurement data, resulting in extra classical noise, which decreases our measurement precision. So now how to overcome such extra quantum noise? Well, we can put on our quantum noise cancelling headphone, which we call a quantum decoder module, as shown in this plot. What the decoder does is that it generates some additional quantum noise, which via destructive interference exactly cancels the extra quantum noise in the sensor output field. And in order to achieve so, the dynamics of the decoder has to be designed in a proper way. Its Hamiltonian and jump operator, HD and JD, actually is dependent on the dynamic parameters of the sensor. We managed to derive a universal formula that relates the dynamic parameters of the decoder to that of the sensor, as written here. You can see it is basically a similarity transformation. Here, HNH is the non-Hermitian Hamiltonian of the sensor, as constructed from its Hamiltonian and jump operator. And T denotes matrix transpose. R is a similarity transformation consisting of a unitary 1 times the square root of the steady state density matrix of the sensor transposed. So forget about all the mathematical details. What this formula tells us is that as long as we know the Hamiltonian and the jump operator of the sensor, we can readily calculate its steady state and then input it into this formula to find the corresponding decoder parameters. This provides us a universal method to achieve the optimal precision of continuously monitored quantum sensor. We have applied a formula to a few example sensor models. Some recovers known result and some predict new opportunities. For linear amplifiers, that is basically a driven dissipative harmonic oscillator, such as in the gravitational wave detector, the corresponding decoder, after using a formula, is a negative frequency oscillator. And this is actually a classical result first conceived by the pioneer of quantum measurement theory, Karl Caves. And experimentally, there are multiple laboratories are trying to realize such a negative frequency oscillator. For example, in the group of Eugene Polczyk at Niels Bohr Institute, he implements such negative frequency oscillator with the collective internal spin of atomic ensembles. Here, the oscillator oscillation frequency corresponds to the detuning between the driving laser and the atomic transition frequency. So it can be very conveniently tuned both positive or negative. For nonlinear quantum sensor devices, as simple as a driven dissipative two-level emitter, the corresponding decoder is also a driven dissipative two-level emitter with almost the same parameters, but an inverse detuning. And for driven dissipative many-body sensor, for example, a transverse Ising chain interfaced with quantum light via its collective spin operator, the corresponding decoder is also a transverse field Ising chain, but with an inverse transverse field. Such a noise-canceling approach can eliminate the dynamically generated quantum noise in the measurement process, but it cannot remove all the quantum noise. There is still the intrinsic quantum noise associated with the quantum particles of the setup. In order to suppress them, we need to generate some quantum correlation between the particles. And our approach is based on an intrinsic property of quantum many-body systems, namely criticality. We further take into account the driven dissipative nature of continuously monitored sensor device. For such a driven dissipative open system, the associated criticality is called the dissipative criticality. A dissipative critical point is a special point in the parameter space that separates two macroscopic phases of the steady state of the sensor. And it is characterized by the closing of the gap of the Liouville operator governing the open dynamics of the sensor in the thermodynamic limit. Close to criticality, the open many-body system becomes strongly correlated, and such strong correlation provides a mechanism to suppress the collective quantum noise. And moreover, in the neighborhood of the critical point, the dynamic and the static property of the open many-body system develop universal scaling behavior as captured by a few critical exponents. And remarkably, we found that the optimal precision of the sensor device, as represented by the so-called quantum Fisher information, also develops such universal scaling behavior. And the associated scaling exponent can be expressed in terms of the critical exponent of the sensor. So this is what we have found. You can see that the scaling contains two parts, one corresponding to a transient regime where the measurement time is shorter than some characteristic time scale, and the other corresponding to the long time regime where the measurement time is longer than this time scale. In this expression, there are in total three exponents. That is the spatial dimension capital D, now it's the lowercase d, and the dynamic critical exponent z, which quantifies how fast the Liouville gap closes as the sensor approaches the thermodynamic limit. And capital delta is the scaling dimension of the local operator O that couples with the unknown parameter. It characterizes at criticality how fast does the two-point correlator of the operator O decays with the interparticle distance. This three exponent fully characterizes the dominant scaling behavior of the optimal precision at a generic dissipative critical point. In this plot, I compare the predicted precision scaling with the standard quantum limit and the Heisenberg limit. This is a log-log plot, so algebraic scaling manifests as straight lines with the slope revealing the associated scaling exponent. You can see the precision scaling at criticality is very close to the Heisenberg limit and far above the standard quantum limit. This is due to the reduced collective quantum noise at criticality. Importantly, all these scaling exponents can be related to the critical exponent of the underlying critical point, so they are pretty robust. As a take-home message of part 2, quantum noise reduction is the essential key for improving the performance of quantum sensors, and I have introduced you 2 new approaches to achieve this. The first one is quantum noise reduction via destructive interference, and the second one is precision enhancement via driven dissipative criticality. I wish to thank my collaborators on this project, including our former PhD student, Theodor Elias, and the 2 professors of our institute, Susanna Hueger and Martin Plenio. As the last slide of our joint seminar, we wish to invite you to visit us at WUM University. We are a lively theory group working on diverse topics of quantum science and technology, ranging from, as Tobias introduced, quantum metrology via quantum effects to biochemical systems to quantum resource theories. And we're particularly proud of the broad nationality of the members of the group as represented by these colorful discs. Thank you for your attention.
Thanks a lot to both of you for these incredible talks. Let's open now the session again for everyone to ask questions. please, if you have any question, just unmute yourself or raise the hand and just ask whatever you would like to ask. Okay, to kick things off, because honestly I have a lot of questions, but I don't want to take too much time. To kick things off, Martin, may I ask you something very stupid? You showed this vision of analyzing the magnetic flux, for instance, in the brain cells.
Mhm.
So I think every one of us has already seen this idea of implanting a chip to the brain or something like this.
Yeah.
In which way does this compare to this more, let's say, I simply call it now traditional idea of connecting machines to the brain?
It's much better because indeed, so like, I mean, there are these companies that actually have already implanted chips in the brain. But really, I mean, would you want to have a chip implanted in your brain? Probably the answer is not really, unless it's really absolutely essential. So, I mean, for people that have very severe neurological diseases, this might be the only way for them to communicate with the outside. They might take this risk. But if I just want to control my computer, I don't want to have my skull opened and a chip put in. So here the vision is really that these would be sensors that would be on the surface of your skull. So it would really, you could really imagine like putting a little helmet on or something. And there would be many sensors that would be, you know, distributed over the entire area so that you get also better spatial information. And then it would really be a direct magnetic measurement through the skull. So there would be no surgical procedure required. So that's really the advantage. Now, you could say, hey, this exists already, because of course we use squids to do exactly that. So there are these, if you go to a hospital in some cases, and the brain is examined, and there's basically a squid device. It's huge. It's extremely sensitive. And you can actually measure magnetic fields from the brain. But the problem there is that it is actually quite large, because you need cooling, you need liquid helium temperatures, and the standoff distance is very large. So actually this sensor is quite far away. And magnetic fields typically tend to fall off like 1/r cubed or so. So going away, having some distance is really a problem, because you compensate this by the incredible sensitivity of squids, but you want to have a compromise. You want to have a quantum sensor that is robust, that you can put directly on the skull, because that gives you a sensitivity advantage. And then if you can have many, then you can actually use the information from all of them to triangulate things, and you can look much more precisely into the depth of your brain. So I think this is kind of, it doesn't go quite as far as these implanted chips, but it really tries to go as far as possible, or as close as possible, from the outside. Yeah. And so there's a chance that something like, I mean, let's say for sure something like this will work. The question will, of course, be how much of a control can be really achieved by our thoughts. So because then, I mean, there's magnetic signals coming, but you have to interpret them also. And I think that's why it might actually in the end be that you need some AI tools to, you know, train your sensor device, and it might have to be trained for every human, because I can imagine that we are not all identical. Yeah. So but it will become very interesting, and it's very well possible that you can start to then read thoughts from the outside. Maybe initially just very simple ones, like, I mean, I like this, I don't like this, or excitement or not so much excitement, a little bit like functional MRI. But it's not out of the question that one can also do more sophisticated things a long way in the future. Right. And for that, you know, we need just better sensors. That's all that is needed.
Thanks a lot. This perfectly answers my question.
Right.
Are there other questions in the meantime? Okay, if not, I will just continue asking to Dayou this time. Could you maybe
Sure.
could you maybe go back to slide number 6, please?
This one.
Yes. Also here, I have very stupid questions. So you showed these 3 examples where you presented also the decoder Hamiltonian and kick operator. And in all 3 cases, it seems that the decoder is extremely similar, the
Yep.
decoder parameters to the system parameters. Do you know how one can classify systems more broadly? Like when do you expect that the decoder is very similar to what the system does? Or do you also know cases where you know that the decoder Hamiltonian is very different or something like this?
Very good question. So we have this universal formula. We indeed analyze this structure. And what we found, and also established by some other works, is that if the steady state of the sensor is a thermal state, meaning that it can be expressed as a Gibbs ensemble, then one can always choose the similarities transformation such that the decoder is basically a replica of the sensor, and it only involves some, inverse of some sign in the Hamiltonian or the jump operator. But if the sensor is not a thermal state, then in general, the corresponding decoder parameters can be drastically different from the sensor. And in certain cases, it can be quite complex. Does this answer your question?
Yeah, totally. Actually, now that you say it, I think it makes total sense, right? Because only the thermal state has no more information in. So as soon as you deviate from it,
Yes, you can understand it in this intuitive way. Yeah, exactly.
okay, thanks a lot. Yeah. Okay, further questions? I hope I'm not too intimidating to you guys. Even if you think it's a silly question, there are no silly questions.
Anything goes, yeah.
This doesn't exist. Now is your time to ask. Okay.
I'm afraid you have to make another one.
Yeah. Me too. At the moment, I don't have other questions, unfortunately.
I can have a quick question. So this is maybe just a wild throw out there, but so this noise cancellation, is it somehow related to this probabilistic error cancellation that you find in typical quantum computing circles?
So I'm not fully familiar with that. If it is a cancellation of classical noise, then it is not, yeah, although spiritually it's similar. And if it is the cancellation of the quantum noise, meaning that, okay, I have a quantum system, it has some intrinsic quantum fluctuation. Now I introduce an ancillary system, which I engineer such that the quantum fluctuation of the ancilla somehow can interfere with the quantum fluctuation of the system. Then this is spiritually similar to what we are doing here. So here the noise cancellation is really, the quantum interference.
Yes, I think, yeah, sorry.
No, please carry on.
No, I think you're right that this probably relates more to classical noise rather than quantum noise, but it's classical noise on quantum processors, which is probably why.
That's true, but it might still, because I mean this probabilistic error cancellation, I mean this is in the family of error mitigation techniques, right? So it might actually be interesting to look more generally what error mitigation can actually do for metrology. So these error mitigation techniques, I mean, so basically in the end, extrapolating to zero noise, whether this can actually make a difference in quantum metrology. My gut feeling would be that probably not, but I'm also not completely sure. Yeah.
So my intuition on this point would probably be that as long as you need averaging, then stuff like Heisenberg scaling doesn't really matter all that much anymore. So if you have to repeat experiments many times to get information, then this is typically what these mitigation processes are around. Then probably not, but yeah.
True, but I mean, you could imagine that you have a situation, let's say your noise is really stationary. So you characterize kind of your noisy environment once. For that, you make a lot of effort, a lot of repetitions and so on. But then subsequently, you somehow can use this to subtract that pre-measured noise from the signal that you're then getting. So maybe that could work. I mean, you are completely right. If every time we first have to characterize the device, then we need so many measurements that it's probably better to invest all of those directly into measuring the parameter. But maybe maybe systematic noise sources and so on can be eliminated in that way. That could be, yeah. So actually, I'm not sure whether people, do you know whether people have done zero noise extrapolation in metrology?
No.
Uh,
I know there are some proposals for error correction for metrology.
sure.
For error mitigation for metrology, I'm not aware of relevant such.
My only concern would be that maybe this is already somehow included in the quantum and Fisher information somehow. But still, might be worth a thought to have a look whether one can do something there. Okay, nice one.
All right, thank you.
Mhm.
Further questions by the audience? I mean, it could also mean that it was simply so clear, which personally I found. Okay. I have the feeling that there are no more open questions left. So therefore, let's thank our two speakers of today again.
Thank you.
Pleasure. And I think it was really, really, really good presentation in the sense that I could understand the first part perfectly. And yeah, have a great day. You will find this talk online on YouTube next weeks. And I hope we see each other again for the next qmeets, which is roughly in 1 month. All right, thanks a lot, and see you next time.